So this last video is tackling the type of problem where it's related rates like our other problems have been, but instead of being directly related to one another, they are indirectly related. So the problem in the video is a balloon is being filled with helium at a rate of 4 feet cubed per minute. That should be an exponent right there. So that's given. And then it's asking us to find the rate in square feet per minute at which the surface area of this balloon is increasing at the instant when the volume is 32 pi over 3 feet cubed. So we're going to be dealing with two things here: the volume of this balloon and the surface area of this balloon. The first thing we always try to do is to determine what it is that we want. And so if we recall, we are being directly told to find the rate in square feet per minute at which the surface area is increasing. So it might help us to give this surface area a name. So maybe we'll just call it S. And so we're trying to figure out the change in surface area with respect to time. So what we want to find is the ds dt. The other thing we have to determine is what we know. So if we look back to the problem, it told us that the balloon was being filled with helium at a rate of 4 feet cubed per minute. So that is basically telling us really the volume, because again, I've got this feet cubed. And so whenever you have like 3 dimensions, a third dimension, that implies volume. And it's the rate of change of volume. It's feet cubed per minute. And so really what I'm being told here is that the change in volume with respect to time is equal to 4 feet cubed per minute. So now we need to connect what we know with what we want. And so we know that dV dt, the change in volume with respect to time, is 4. And we want to find the change in surface area with respect to time. So what we need to figure out is if there's some kind of formula that relates volume to surface area. And in fact, there is no such formula. But in both of the formulas for volume and surface area, they both involve the radius of the balloon. The radius of the balloon sort of indirectly relates the volume of the balloon to the surface area of the balloon. And you could think of this balloon as being in the shape of a sphere. Think of the balloon as being in the shape of the sphere. And then what I can use is the formula for the volume of a sphere. Formula for the volume of a sphere is 4/3 pi r cubed. And then I could use the formula for the surface area of the sphere. And the surface area of the sphere is 4 pi r squared. So what you can see here is that the radius of this sphere, or of this balloon, if you will, is the link. The radius is the link between volume and surface area. So if I can find dr dt, the change in radius with respect to time, even though I wasn't asked to find that, but if I can find dr dt, then I could easily find ds dt. So this will be our indirect link between what we want and what we know. Now, let's start with the volume formula, and we'll differentiate both sides of that with respect to time. Okay, so here's our volume formula here. Volume of a sphere, which we're going to let our balloon have the shape of a sphere, in terms of the radius of that sphere. Now I want to take the derivative of both sides with respect to time. So the derivative of volume with respect to time would simply be dV dt. Then on the right side over here, I'm going to take the derivative of 4/3 pi r cubed with respect to time. So I have to use the constant multiple rule because of this constant being multiplied to the function. I'm going to have to use the power rule since it's r is being raised to the third power. And I'm going to have to use the chain rule because r is changing with respect to time. It's a function of time. So I'm going to also have to multiply by the derivative of r with respect to time. So to do the power rule, basically the 3 would come down in front here and get multiplied to the 4/3. So that would just leave me with a 4. And then of course I just leave the pi there because pi is just a constant. And it'd be r squared since you subtract 1 from the power of 3 to get power of 2. So that was the power rule and the constant multiple rule right there. But now I have to multiply that by the derivative of r with respect to time because I'm differentiating with respect to t, not with respect to r. So notice I'm not finding dv dr, in which case I'd be done before this. I'm finding dv dt, the derivative of volume with respect to time. So I have to differentiate this with respect to time. Okay, so now I have an expression relating the change in volume with respect to time to the change in radius with respect to time. And as you recall, I was given a value for the dv dt, or I was told that that helium was entering the balloon at a rate of 4 feet cubed per minute. So I know that this value of dv dt is equal to 4. Okay, now I also need to figure out a value for r. If you recall earlier in the problem, it mentioned that it wanted us to find the change in surface area with respect to time when the volume was 32 pi over 3. I can use that in conjunction with this formula up here to figure out what r would have to be at that same instant. So again, I'm looking at the instant where volume is 32 pi over 3. So I'll plug that into the volume formula. So the volume formula is volume of the sphere is equal to 4/3 pi r cubed. So then if I set the 32 pi over 3 or substitute that for v, I'd get 32 pi over 3 equals 4 pi over 3 r cubed. Then if I multiply both by the reciprocal, which would be 3 over 4 pi, I could cancel out everything here on the right, and on the left I'd just be left with 8 because the 3's would cancel, the pi's would cancel, and 4 goes into 32 8 times. So I'm left with 8 equals r cubed, and so then that leaves me with the radius must be 2 at the instant when the volume was 32 pi over 3. So going back to our original equation, which was dv dt equals 4 pi r squared dr dt, now I could substitute again the 4 for dv dt, and now I can substitute the 2 for the radius, because at the instant that the volume was 32 pi over 3, at that instant the radius is 2. And so now I'm able to solve for dr dt because I have that 4 is equal to, let's see, this would be 4 right here. 2 to the squared is 4. 4 times 4 is 16. So I get 4 is equal to 16 pi dr dt. And then I'll divide both sides by 16 pi to get that to cancel. And so I end up with dr dt is equal to 1 over 4 pi. And that would be, or I guess, feet per minute. 1 over 4 pi feet per minute. Okay, so now I found dr dt. This is the link right here. This is huge. I have found the link between volume and surface area. So now I have to relate the radius to the surface area. And that's just the formula for the surface area of a sphere. So again, the surface area of the sphere is 4 pi r squared. Well, I'm just going to take the derivative of with respect to time of both sides, just like I did with the volume. Well, the derivative of surface area with respect to time is simply ds dt. And then the derivative of 4 pi r squared with respect to time would simply be, so I'm going to do power rule, so the 2 gets multiplied to the 4, so I get 8 pi r to the first power times dr dt, since I also have to take the derivative of radius with respect to time. Okay, so in the last part of this, we found the radius to be 2 at the instant the volume was 32 pi over 3, and we found dr dt to be 1 over 4 pi at the instant that the volume was 32 pi over 3. So I then can simplify or find that the change in surface area with respect to time will simply be 8 pi times 2 times 1 over 4 pi. And then that will reduce down to 4 because the pi's will cancel. The 2 will cancel with this 4, leaving me with a 2. And then 8 divided by 2 is 4. So the change in surface area with respect to time is 4 feet squared per minute. But now we don't want to forget to go back and answer the question. We have our work. Recall what the question was asking. It says the rate in square feet per minute at which the surface area is increasing when the volume is 32 pi over 3 feet cubed is, and we would say the rate is 4 square feet, because remember we wanted the square feet per minute, 4 square feet per minute. And we have successfully completed this problem, and I will see you all in class.